Circuit breakers are commonly employed to switch motor circuits. Their functionality extends beyond simple overcurrent protection, as they can also serve as a switching mechanism for controlling motors. The utilization of circuit breakers for motor circuit switching offers several advantages. Firstly, it provides a dual-purpose device, consolidating both overcurrent protection and switching functions into a single component. This consolidation can lead to space savings within electrical panels, as separate switching devices like motor starters may not be required in certain applications. Secondly, the use of circuit breakers for motor switching can simplify the overall circuit design and wiring, reducing the number of components and connections. This simplification can enhance reliability and reduce the potential for wiring errors. Thirdly, circuit breakers are readily available and widely understood by electricians and electrical engineers, making their application for motor switching a familiar and accepted practice. However, it is important to consider certain factors when using circuit breakers for motor switching. Firstly, the circuit breaker must be properly sized to handle the inrush current of the motor. Motors typically draw significantly higher current during startup than during normal operation. The circuit breaker must be able to withstand this inrush current without tripping, while still providing adequate overcurrent protection for the motor. Secondly, the circuit breaker must be rated for the intended switching frequency. Frequent switching can cause wear and tear on the circuit breaker contacts, potentially reducing its lifespan. If the motor is expected to be switched frequently, a circuit breaker specifically designed for switching duty should be selected. Thirdly, the circuit breaker must be compatible with the motor control scheme. Some motor control schemes may require specific features or functions from the switching device, such as the ability to be remotely controlled or interlocked with other equipment. The circuit breaker must be able to accommodate these requirements. In general, circuit breakers are a suitable option for switching motor circuits in many applications. However, it is important to carefully consider the factors mentioned above to ensure that the circuit breaker is properly selected and applied. Consulting with a qualified electrician or electrical engineer is recommended to ensure that the motor circuit is designed and installed in accordance with all applicable codes and standards, such as the National Electrical Code, also known as NEC. The selection of a suitable circuit breaker for motor applications depends on several parameters. One must consider the motor's full load current, or FLA. This is the current the motor draws under normal operating conditions at its rated horsepower and voltage. The FLA can be found in the motor's nameplate. A suitable circuit breaker must have an amperage rating that is greater than the motor's FLA. This ensures that the breaker does not trip unnecessarily during normal motor operation. The NEC provides guidelines on the maximum allowable overcurrent protection for motor circuits. These guidelines are typically expressed as a percentage of the motor's FLA. The selected circuit breaker's amperage rating must not exceed these limits. Motor starting current, often significantly higher than the FLA, is also important. Motors draw a large inrush of current during startup, which can be several times the FLA. Circuit breakers must be able to withstand this inrush current without tripping. Time delay circuit breakers, also known as inverse time breakers, are often used for motor circuits because they allow for short duration overloads such as those experienced during motor starting without tripping. These breakers have a built-in delay that allows them to ride through the inrush current. The interrupting rating of the circuit breaker must be greater than the available fault current at the point of installation. The interrupting rating is the maximum amount of current the breaker can safely interrupt during a short circuit or ground fault. If the available fault current exceeds the breaker's interrupting rating, the breaker may fail to clear the fault, potentially leading to equipment damage or personal injury. The voltage rating of the circuit breaker must be equal to or greater than the voltage of the motor circuit. Using a breaker with a low voltage rating can result in the breaker failing to operate properly or even exploding. The circuit breaker must be suitable for the environmental conditions in which it will be installed. This includes temperature, humidity, and the presence of corrosive substances. For example, if the breaker is installed in a damp location, an M4 or 4X rated enclosure may be required. The horsepower rating of the circuit breaker is another consideration. Some circuit breakers are specifically rated for use with motors and have a horsepower rating that indicates the maximum motor size they can protect. The circuit breaker must be listed by a recognized testing laboratory such as Underwriters Laboratories, also known as UL. This listing indicates that the breaker has been tested and meets applicable safety standards. When selecting a circuit breaker for motor applications, it is essential to consult the NEC and other applicable standards. These standards provide detailed requirements for motor circuit protection and can help ensure that the circuit breaker is properly selected and installed. Coordination studies can also be performed to ensure that the circuit breaker is properly coordinated with other protective devices in the system. Coordination helps to minimize the extent of any outages by ensuring that only the effective portion of the system is de-energized during a fault. Motor starters are electromechanical devices that provide a safe and reliable way to start and stop electric motors. They typically consist of a contactor, which is an electrically operated switch, and an overload relay, which protects the motor from overloads. While circuit breakers can be used to switch motor circuits, motor starters offer several advantages, particularly in larger motor applications. Motor starters are designed specifically for the frequent starting and stopping of motors. The contactor in a motor starter is designed to withstand the high inrush currents associated with motor starting and can handle frequent switching cycles without premature failure. Overload relays provide more precise overload protection than circuit breakers. Overload relays are designed to trip out a specific percentage of the motor's FLA, providing better protection against prolonged overloads that can damage the motor. Motor starters often include additional features, such as undervoltage protection, phase loss protection, and remote control capabilities. These features can enhance the safety and reliability of the motor control system. In some applications, a combination of a circuit breaker and a motor starter is used. The circuit breaker provides short circuit and ground fault protection, while the motor starter provides overload protection and motor control functions. This combination provides a comprehensive protection and control solution for motor circuits. There are different types of circuit breakers commonly used in electrical systems, each with its own characteristics and applications. Standard thermal magnetic circuit breakers are the most common type of circuit breaker. They use a combination of thermal and magnetic elements to trip the breaker in response to overcurrents. The thermal element responds to sustained overloads, while the magnetic element responds to short circuits and ground faults. Instantaneous trip circuit breakers, also known as magnetic-only circuit breakers, trip instantaneously in response to high magnitude overcurrents. They do not have a thermal element and are typically used for protecting sensitive electronic equipment. Ground fault circuit interrupters, also known as GFCIs, are designed to protect people from electric shock. They detect small imbalances in current between the hot and neutral conductors and trip the breaker quickly to interrupt the flow of electricity. Arc fault circuit interrupters, also known as SIs, are designed to protect against fires caused by arcing faults. They detect the unique electrical signatures of arcing faults and trip the breaker to interrupt the flow of electricity. Molded case circuit breakers, also known as MCCBs, are a type of circuit breaker that is enclosed in a molded case. They are available in a wide range of sizes and ratings and are commonly used in commercial and industrial applications. Insulated case circuit breakers, also known as ICBs, are similar to MCCBs but have a higher interrupting rating. They are typically used in high current applications. The National Electrical Code, or NEC, is a widely adopted standard for the safe installation of electrical wiring and equipment in the United States. It is published by the National Fire Protection Association, also known as NFPA. The NEC contains detailed requirements for the protection of motor circuits, including the selection and installation of circuit breakers and motor starters. The NEC specifies the maximum allowable overcurrent protection for motor circuits based on the motor's FLA and the type of motor. It also provides guidelines on the selection of circuit breakers with adequate interrupting ratings and voltage ratings. The NEC requires that motor circuits be protected against short circuits, ground faults, and overloads. Short circuit protection is typically provided by a circuit breaker or fuses. Ground fault protection is typically provided by a ground fault circuit interrupter or ground fault relay. Overload protection is typically provided by an overload relay in a motor starter. The NEC also addresses the coordination of protective devices in motor circuits. Coordination ensures that only the affected portion of the system is energized during a fault, minimizing the extent of any outages. Proper motor selection is also crucial for reliable operation and protection. Selecting the right motor involves considering factors such as horsepower, voltage, speed, and enclosure type. The motor's horsepower rating must be sufficient to handle the load it will be driving. The motor's voltage rating must match the voltage of the power supply. The motor's speed must be appropriate for the application. The motor's enclosure type must be suitable for the environmental conditions in which it will be installed. Regular maintenance of motor circuits is essential for ensuring their continued safe and reliable operation. Maintenance tasks include inspecting circuit breakers and motor starters for signs of wear or damage, testing circuit breakers to ensure they trip properly, tightening electrical connections, and cleaning motor enclosures. Infrared thermography can be used to detect hot spots in motor circuits, which may indicate loose connections or overloaded components. Regular maintenance can help to prevent electrical failures and extend the lifespan of motor circuits and equipment. Motor control centers, also known as MCC, are commonly used in industrial and commercial facilities to centralize the control and protection of multiple motors. An MCC typically consists of a metal enclosure containing individual motor starters, circuit breakers, and other control devices. MCC offers several advantages, including space savings, simplified wiring, and centralized control. They also provide a convenient way to monitor the status of motors and diagnose problems. Variable frequency drives, also known as VFD, are electronic devices that control the speed of AC motors by varying the frequency of the power supplied to the motor. VFD can improve energy efficiency, reduce motor wear and tear, and provide precise speed control. They are commonly used in applications such as pumps, fans, and conveyors. When using VFD, it is important to ensure that the motor and VFD are compatible and that the VFD is properly programmed to protect the motor. Harmonic distortion is a potential problem associated with VFD. Harmonic filters may be required to reduce harmonic distortion and prevent damage to other electrical equipment. Surge protection devices, also known as SPD, are used to protect electrical equipment from voltage surges caused by lightning strikes, switching operations, and other events. SPD should be installed on motor circuits to protect circuit breakers, motor starters, and other sensitive electronic equipment. Grounding is an essential safety measure for electrical systems. Proper grounding provides a low impedance path for fault currents to flow back to the source, allowing protective devices to quickly trip and clear the fault. Motor circuits should be properly grounded in accordance with the NEC. Electrical safety is paramount when working with motor circuits. Only qualified electricians should perform electrical work. Always energize circuits before working on them. Use appropriate personal protective equipment, such as safety glasses, gloves, and insulated tools. Follow all applicable safety procedures and regulations. Electrical hazards can be deadly. By taking precautions and following safety guidelines, it is possible to work safely with motor circuits and avoid electrical accidents. Motor efficiency is an important consideration for reducing energy consumption and operating costs. High-efficiency motors are designed to convert a larger percentage of electrical energy into mechanical energy, reducing energy losses. Upgrading to high-efficiency motors can significantly reduce energy costs over the lifespan of the motor. Power factor correction can also improve motor efficiency. Power factor is a measure of how effectively electrical power is being used. A low power factor indicates that a significant portion of the electrical power is being wasted. Power factor correction capacitors can be installed to improve the power factor and reduce energy losses. Load calculations are performed to determine the total electrical load of a building or facility. Load calculations are used to size electrical service equipment such as transformers, switchgear, and circuit breakers. Accurate load calculations are essential for ensuring that the electrical system is adequate to handle the anticipated load. Single phasing occurs when one of the phases in a three-phase motor circuit is lost. Single phasing can cause the motor to overheat and fail. Phase loss protection relays can be installed to detect single phasing and protect the motor. Testing of circuit breakers is important to ensure they are working properly.